Right, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today, I would like to continue our course on fatigue and fracture mechanics. Lecture 6, stress analysis of members with cracks. Okay, today outline will be on the superposition of stress intensity factors, and then we're going to cover about the stress field ahead of crack tip. Okay, let me see on the superposition of stress intensity factors. Components that contain cracks may be subjected to one or more different types of mode 1 loads, such as uniform tensile loads, concentrated tensile loads, and the last one, or bending loads. The stress field distributions in the vicinity of the crack tip subjected to these loads are identical. Like we have covered in the previous lecture, we technically can measure and calculate how much is the sigma x, sigma y, shear xy, and sigma z based on the, the assumption that we apply on the previous lecture. Okay, consequently, the total stress intensity factor can be obtained by algebraically adding the stress intensity factors that corresponding to each load. Okay, what they mean in this sentence is actually it can be obtained algebraically. Means that you uh, on the one situation, you might not calculate the whole thing based on one calculation. It is actually a combination on several type of stress intensity factors. So if the question is giving you in terms of one complex crack uh, geometry, in which you cannot determine that by one single calculation, you have to separate that and then combine for each stress intensity factors. Okay, let me see on this example. Okay, this is an example one, plate with an edge crack subjected to tension plus bending loads. Okay, let's see this one. This is a plate with a edge crack tip where we determine that as A. And then the width of the plate is measured as 2B. It is subjected to tension loads, equivalent tension loads. Right, and then the plate is also mentioned plus the bending loads. Okay, okay. Now we need to plus with another mode, which is bending loads. Right, if you see, this is positive value, but it is almost half of the value from the tension load. And then it will be negative, means that there is some kind of uh, bending motion. Alright, if we add this algebraically, you might see that in one single mode, which is, let's take this as 2, value 2, while this is 1. Means that once you added this point and this point, it will become 3. Just like shown in this figure. Okay, let's see the last one. The last point, this is 2 and then this is negative 1, for example, negative 1. Means that it will be 1. That's why you can see here the magnitude is a little bit lesser compared to the previous one. So they can plot this together. That's why we said just now it is a combination or algebraically added to each another. Okay, the same what happened to the opposite side. Okay, how to calculate the stress intensity factor? In this case, the K1 total is actually K1 of the edge crack situation under the tension load, and then the edge crack under the bending load. Here we need to add the K1H as we learned in the previous lecture, and then we just add the value or insert the value in term this into this equation, while it need to be plus with the K1 or the stress intensity factor due to bending, as also we have covered this in the previous class. Only by doing this you can calculate for the total stress intensity under this load subjected to tension plus bending loads. Okay, let's see in this case. A fairly common situation is a plate loaded in tension at one end and this force being withstood by a bulk force P. If you see the situation at this end, it is constrained or we fix at this point. Means that it is on we only have one tension load at one end here. Okay, the crack is in the middle and this force being withstood by a bulk force P. Okay, in this situation, you need to uh, break that into several factors, like in this case, a crack in the middle, and then you have tension loads here. At both sides, plus with a crack where you have two bulk force P, and then you need to minus a situation where you have a crack and then only one situation of 1P force bulk, because it is mentioned here the tension the plate is loaded in tension at one end, so you need to minus or you need to remove the load at this end so that you only have one end. Okay, so it means that these two will be coupled to each other by adding this situation but minus this situation, because you need to remove the one end. Okay, and also withstood by a bulk force P, so you need to cancel this part, only you have this part. Okay, by doing this, to get the whole stress intensity factor, you need to add this situation, the stress intensity factor due to this situation plus with this situation, and then minus this situation. Only that you can calculate for this situation. Okay, in another situation, the solution K1 is a superposition of K1 solution for a true thickness crack and a crack subjected to points load. If this is the case, like usual, like the same that we have covered just now, I have a crack in the middle, and then one the what we call the load is in the one side and the other one is fixed. While if you see in this case, I have a hole here uh, withstand by a load P as well, a bolt, sorry. Okay, this is the end, while I have another stress in this or tension in this direction. Okay, is this actually equivalent to a plate where you pull that by both sides, and then you have a crack in the middle plus a crack where you have two P force acting on the bolt force. Okay, so here the stress intensity factor for this plus in this case is actually equivalent to this case plus this case. You just need, and then later on, you just need to substitute both of the situation. Okay, why they say this K14 in this case here plus K11 is actually the same like in the previous solution. You just equivalent this, it become 2K1, K11, and then you can divide the summation of both situation, you can divide by 2. And then you can get what is the superposition situation for K11. Right? Okay, the superposition of stress intensity factors, for example 2, thin wall pressure vessel subjected to a hoop stress. Hoop stress, in this case, uh, is symbolized by a sigma and then a small hoop here. So we say that this as sigma hoop. And the crack surface subjected to the internal pressure P. I have this type of structure. The stress hoop make this pressure vessel a little bit bend, and then I have internal pressure inside. Let's consider this is a case, and then you have internal pressure like gas or something that pushing the surface of the body. So you due to the crack thickness, uh, internal crack surface, and then the crack also consists of thickness. So we can draw this as this one, the length of this diameter of the crack, and then the depth of the crack as A. The combined stress intensity factor for this case, for that case is K1 equal to K1 hoop due to the hoop stress plus K1 due to the pressure. So you have two situations. You need to consider both situations, only then you can calculate the whole stress intensity factor for the crack edge pressure vessel. After that, you just substitute according to the situation. Alright, this is almost like the same before, but this is we now consider a smaller or discrete situation where we want to study the stress field equation near the crack tip. Whatever we have learned before is just on the crack, but now in the crack tip. The crack tip means at the edge of the crack, near to the edge of the crack. So, if I have a situation like this is my structure or my plane. I have a crack where this is my force or this is my tension load, for example, acting on this surface. So I have an opening mode 1 crack. Okay, near to the crack tip means that at the edge of the crack, in this case is here, I can measure what is the radius of R to any position here, any position on this plate. And then I can measure what is the angle due to the X plane. If you want to calculate what is delta X for at that location, delta X, delta Y, XY, you can just substitute the value that you have chosen on this surface, and then you can substitute everything and get the value for each of the term. Okay, it will also mention that sigma ij equal to k1 divided by square root of 2 pi r times f ij due to theta. Okay, this is the correction factor plus the higher order terms. Means that if you have Fij power of 2 and so on. Means that it will be more complex numbers. Okay, K1 is called stress intensity factor. In this case, we just substitute the whole value to get this magnitude of each term. Okay, stress field equation corrective also if mentioned that if the R is less than A, R means the radius to wet position you want to calculate less than the crack length A, the elastic stresses in the vicinity of a crack tip can be very large. We can see here if R is less or small r value of R here, you might get higher stress value of stress. In reality, such high stress magnitude do not occur because the material in this region undergoes plastic deformation, thus creating a plastic zone that surrounds the crack tip. Okay, in reality, like we have defined last time, in the situation of an elastic region, at any point, once the load been released, it will return back to its state, its original shape or its original state. But once you go beyond that, which is you are now in the plastic region, you cannot undergo. Otherwise, it will. You can once you release the load, it couldn't go back to its original position. So the same like the crack tip. Once you have the crack tip has achieved the value, and then the crack tip now is propagating or enlarged, is no more on that original position. Once you release the load, of course the crack tip won't go back to the initial position. So that's why we say the crack tip in this region, material in this region will undergo plastic deformation. Okay, where it also creates a plastic zone surround the crack tip. Okay, in the event of calculating the crack tip stress, it can be visualized with this trend or this graph. If I have a crack tip length with 2.2a, this is the crack tip, crack length, while this is our crack tip. If you can see based on this trend, the yield stress will be maximized, will be the maximum value near to the crack tip. While if you take a far away location, it will be lower. Okay, it can be visualized, it can be determined by using this equation. If you see the sigma yield equal to this equation, this relationship, divide K1 divided by square root of 2 pi r. R here means the location or the distance of the point that you want to measure with respect to the origin of the crack tip. So the lower value of R will be a higher value of sigma y. If you take this point, for example, this is 0.1, this is 0.2, up to here it will be 1. So higher value of R will just decrease the value of sigma y. Okay, we understand that the crack tip near to the surrounding of vicinity of the crack tip will be a plastic region. So in this case, you can visualize by this figure. Okay, near to the crack tip, which is surrounding of the crack tip, it will be RP, the plastic region of the crack, the length of the R. Okay, beyond that, only it will be elastic. Okay, you can measure this by using this equation, sigma ys, yield stress, equal to K1 divided by square root of 2 pi R asterisk P. Okay, this is the value of Rp within this region. Okay, Rp can be measured, or you can calculate that by using this equation. So you just substitute what is K1, what is 2, what is pi, what is sigma yield stress of this of that particular material. You can get what is Rp. But it must be reflected to A, equal to, if you want to change K1 in terms of this equation also can, where you need to remove pi as well, and then you just substitute what is, how much is your crack length. So you can get Rp. Only by doing that you can determine how much or how large your plastic zone at the crack tip. Okay, this in this situation A here, while this is B, the graph is assumed as the stress distribution, while B is approximate stress distribution. Okay, this is assumed stress distribution. Okay, the shape of the plastic zone. Uh, you need to represent this in terms of two plane. Either it will be plane strain or plane stress. How could we determine this? If I want to calculate for Ry theta for plane stress, I need to use this equation. While if I know, I want to know how much is the region or how much is the distance of Ry due to the plane strain, I need to use and apply the parameter value into this equation. Only by doing that, you know what is your Ry theta for the plane strain and then Ry theta for the plane stress. You know how large it will go. And then you can plot the surrounding value uh, of that region. Stress. This is the same. The stress field equation for the near crack, the crack tip. The same situation where you have applied stress here. This is the sigma u stress. The only limit that you have to apply in your elastic region. Once beyond this, you will be plastic region. Okay, to Ry, once you determine the value, what is Ry in this case, you can determine the plastic zone like we have covered in this slide. Rp here. Okay, once you get this, you can plot how much is the elastic stress distribution, and then the stress distribution after local yielding. Okay, the size of the plastic zone Ry is given by these two terms. Either you want to calculate that for the plane stress condition, Ry under the plane stress condition, or Ry for the plane strain condition. Okay, where this is the schematic representation of the variation of plastic zone size along the front of a crack in a thick specimen. Means that if I have a thick specimen, it is no more 2D, but it will be 3D specimen. So if I have the crack tip, in this case, will be located here, I can plot a 3D situation where this is will be my X plane, and then the height will be determined by y plane, and then the width of the surface will be the z plane. Okay, the mid section means that you can cut in this plane. You cut once you cut this, you can actually represent that everything into the each view. Okay, if how you can determine the what we can get from the edge view. Actually, once you have the crack tip, you can determine where is the location of the plane strain mode 1. In this case, this is the smallest one, the smaller region compared to the plane stress mode 1. Okay, because this what we call the structure here is actually we have several type of thickness. So I have a thickness along this direction. So the plane strain mode is the lower one, while the bigger one here in this case will be the plane stress mode 1. Okay, R1 can be determined by using this formula. The same, you just substitute the value. What is K, the stress intensity factor, and then sigma U stress. Okay, this is the representation of the machine notch, fatigue crack, plastic zone, and then the plane strain region, plane strain, and then plane stress, at what region it is. Everything has been summarized into this schematic diagram. The effective K1 factor for large plastic zone size, like we discussed before in the previous slide or previous lecture, the crack length is represented by 2A. But actually, if you want to have what we call an effective crack length, actually you need to add the crack with the diameter or the radius of the crack length, the crack tip. Sorry. So the effective crack length is actually represented by this equation, by this parameter 2a EFF effective equal to 2a the crack length plus 2r y the crack length, the crack tip length. Okay, you can see that in this figure. Once you have a structure, in this case here, sigma is the how much is the stress you apply to the structure, and then the crack length is actually 2a plus the crack tip 2ry, the value here. So only by doing this you will get 2af. Therefore, if you want to calculate for the effective uh, stress intensity, in this case it is for the large plastic zone size, you need to use the same formula but replace A with A effective. The same formula, K1, but this is effective equal to sigma applied, how much value of the stress that you applied here, times square root of pi A effective, the value here. Okay, K1 in this case, if we solve the this equation, they implement that into, or they briefly expand 2AF to A effective here, as in this case, actually you can transform this equation to this equation. You just need to expand what is A effective and then represent it by this parameter, the whole thing here. Okay, solving for K1 effective, we get this equation. So you just need to apply everything that you see here. What is sigma applied? You just substitute here. What is your crack length? 2A divided by 2, and then what is your applied stress here again, divided by the sigma yield, you will get the value for stress intensity of the effective stress intensity factor for the large plastic zone size. Okay, for the K contrafracture, if you see K1 is characterize the crack tip condition, even though the 1 divided by square root of R singularity does not apply to the plastic zone. So LEFM, the linear elastic fracture mechanics, cease to be valid when the plastic zone size becomes large relative to the key dimension. Okay, the situation here, you can see in this case where, let's say this is the specimen, the test specimen, where I have a two hole here in this on that specimen, and then we pull this location with a tensile load in the opposite direction. Of course, you will have an opening mode here, and then this is the crack length starting from this point to this point, and then surrounding of the crack tip, you can actually get how much is the plastic zone surrounding the crack tip, or vicinity of the crack tip. Okay, they plot this the sigma yy here based on this situation, and then they get the log value, the linear elastic region, by using this plot. So it just a representative for the plastic zone A, and then the representative for and then the surrounding, or from point R to what extent it will become a singularity dominated zone. Okay, so this is they compare these two. If you see, there is two curve here. The test, this is the curve for the test specimen where we have discussed this part, while this is a bigger one, bigger plot due to the structure in which is represented by this figure. So they just take these 2 points, these two illustration from the point of structure, and then from the point of the test specimen, and then they get both coincide to each other, and then represented the same at the same point for the plastic zone. Okay, to find, there are two, in this case, we need to, I'm going to introduce you to the technique on how could you calculate, or most likely we use that in the fracture mechanics. J integral and CTOD. Okay, these are two other fracture mechanics parameters that can be used to calculate driving forces for fractures. For the J integral, it will be path independent parameter. While CTOD, most likely we represent that with delta I1, the crack tip opening displacement. So delta here means actually it is a displacement. These are used to estimate the fracture characteristic of materials exhibiting elastic plastic behavior. So this is just the formula for J integral. For linear elastic behavior, the J integral is identical to G. G is the energy release rate that we have covered last time. The energy, they also mentioned here, the energy release rate per unit crack extension. Okay, this is the equation that you need to apply if you use the J integral. 1 minus mu square, mu is the positive ratio, times K1. K1 is the stress intensity factor for that particular structure, and E is the elastic modulus. So you can rearrange this to find what is K1 for the plane stress and due to the plane stress using this equation. Alright, means that using the same equation J1 equal to G1 equal to here, you need to decide which one will give you the value for the plane stress and plane strain. Okay, for CTOD, the crack tip opening displacement for center crack in white plate, delta 1 is given by this equation. Delta 1 equal to pi sigma square applied times A, crack length, half of the crack length, divided by E, use stress due to the what type of material. You rearrange everything, and then if you want to change the form from pi, sigma, and crack length, uh, you can represent it with K1. Just change the form to K1. Okay, when we design something, when we want to design something or design a structure, you need to select the maximum flow size dictates the design stress so that we can estimate what is the maximum stress that will be allowed to be applied on the structure. So sigma design should be less than Kc. Kc is the fracture toughness, or we say that as critical fracture toughness, Kc, divided by y uh, square root times square root of pi a max. Okay, so this is once you apply here, you need to make sure that your design always below than this parameter. Only that you will get no fracture within that limit. Okay, case 2. For the case 2, design stress dictates the tolerable maximum flow size. Means that you need to, if you rearrange this equation, you bring that down, up, and so on, and then you need to make sure that A max, the crack length, maximum crack length must be below than this situation. Otherwise, you will have fracture. If you see A max is more than this, so means that your location of your design will be in this region. The same like this one. If you get sigma design higher than this, means that you already in the fracture region. Okay, let's consider this example. If I have a structure that consists of a thickness crack in the middle of the structure, and also I have two sided of tensile load represented by sigma. Okay, the question said consider a true thickness crack in the white plate. Design stress is 108 megapascal and 310 megapascal. So using this equation, actually you can find how much is the tolerable flow size. K1 equal to sigma, which is applied stress, times square root of pi a. Okay, they give you the condition of the structure where the K1C, the critical fracture toughness is 66,132. So you just apply that into this equation. Once you get that, you need to check for the plot here. Where is the location of that design flow size? Either this is beyond this region, which is it will be no plastic yet, based on this no fracture, based on this sketch, or if this is beyond this plot, it will be a fracture situation. Alright. So this is just another question. If residual stresses due to the welding present so that the total stress is 552 megapascal at the crack, what is the tolerable flow size? This is another question that we need to consider for another plot. Okay, for another question for an edge crack in 760 millimeter white plate with sigma yield 280 megapascal. Uh, this is another question. Then in which I believe that you can do this by yourself. Try to find what is the critical crack length for the design for this type of design stress. Okay, and this one. Okay, next topic we're going to talk about the fracture toughness testing on how and what type of machine that we're going to use to estimate the fracture toughness. That's all. Thank you very much for your attention. Let's see if you have any other question. We can discuss in the next lecture. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.